All right, so let's talk about process equations. You kind of use these in some form or another. In the homework you handed in, you actually did it, problem 2. But these are when you're dealing with, you want to find like pressure, density, volume, if you're a gas, between one state to the next. There's shortcuts, okay? So let's look at, these are for gas only. Let's look at constant pressure. What's that mean on a graph if I plot P versus V? Horizontal line, yep. And say we go, it doesn't really matter, 1, 2. If I write the ideal gas for each state, and I say it's constant pressure process, that means P1 equals P2. And you end up getting relationships between density, temperatures, volumes, and those are on your cheat sheet that I gave you. All right, so go from one state to the next. If we know it's a constant pressure process, it means it's an isobaric process. We now have a set of equations that we can use to figure out the relationship between volume, temperature, density, volume. Okay? What is the boundary work in a constant pressure process? What's the boundary work? Yep. Or if we know it's constant pressure process, it's P times the change in volume. All right. And say we want to find Q and only assume there's boundary work. So this case is only valid if there's boundary work. So delta U equals Q plus W. So that's our first law. Q. And these are net values. And what I'm going to do is assume that the boundary work is negative. Okay, so we have something going out, so it's expanding. So when we bring it over to the other side, it becomes a negative, but we know it's going out, so it's another negative. Okay, don't worry about the signs right now. We can break down this to M delta U plus P how to do it, M P times delta V. We're only assuming boundary work, and it's expanding, so the net process is going to be out. And I just plugged in those. I'm going to factor out the M. Anybody know what delta U plus delta P, delta U plus P delta V is? Q is equal to M Cp delta T. No. That is one of the, this is one of the most famous heat transfer equations if your gas in a piston cylinder is expanding, looking at the net heat, okay? But this is only valid if there's boundary work going out and you're looking for Q. All right, so again, I'm just showing you this process. We're going to review these as we go through, but this is only valid for boundary work going out, and you can solve for your Q. So your cheat sheet, I think, has that, right? So go to your process equations, page 2 and page 3. Top of page 3, it has exactly what I just did for you, okay? So if you know that it's boundary work only, you can solve for Q, okay? So what's the next process on the cheat sheet? Volume. So number 2. And did I put what that process is called? Which I think I've talked about it a million times. Isometric. And again, what's that look like on a curve? Straight line down. And I'm not going to go through everything now, just going to give you what the cheat sheet has. It should have these correct. You can find the relationship between pressure and temperature. What is the boundary work in this process? 0. Yep. Because it's straight line downward. And if you did the first law, if there was only boundary work, you get M as CV delta T. You've seen that one, hopefully you too. So you kind of hopefully identified constant pressure. If there's only boundary work, Q is MCP delta T. If it's an isometric process with only boundary work, which is actually 0, okay, there's no other work, your Q is that, which states that delta U is Q, right? Because there's no other work terms. What's the other assumption you're doing? Is this equation's only valid for a gas, okay? So remember that. Okay, number 3, constant temperature. Isothermal. T1 equals T2. And what does delta U equal? 0. Yes, 0. Did I tell you that? I do. Okay. Why does it equal 0? Because there's no change in temperature. That means your internal energy doesn't change. Okay? And we get for our process equations P1 over P2, V2 over V1. And then, actually, that equals little v2 over little v1, which is density 1 over density 2. Your boundary work equation is your constant times ln of v2 over v1, which could be p1 v1 ln of v2 over v1. And your heat, and then I'll make sure I'm doing little q, which you could just multiply by mass. Actually, you need the combination of internal and your boundary work. Yep, because everything is per unit mass. You can find big Q by multiplying by mass. What I'm doing here is showing you and helping you classify when you get to these problems. If you know your process only involves boundary work and it's an isothermal process, you can jump right to these equations. I'm fine with that. But what happens if you have electric, shaft, boundary work, and it's isothermal? Then you can't, right? You're going to add more work terms, okay? So just be aware of that. It helps you identify the key words and give you kind of a shortcut. The last one is polytropic. We on 4, I think. Polytropic. And what does polytropic mean? P times V raised to the n is the constant. And if you looked at a graph, it'd be something like that. Depending on the exponent, it could be more of a curve or less of a curve. And this is probably more realistic than the normal processes like isometric, okay, isothermal, whatever. It's just kind of one step closer to the actual real thing, okay? And I'm not even going to go through these, but I'll just write the first one. Like these should be in your cheat sheet, aren't they? Blah, blah, blah. I hope they are. Yeah. So, I mean, you have the idea here. Polytropic, yeah. Page 4, I give you all those process equations, and I give you the boundary work, okay? Now Q, you just have to plug everything back in once you find your stuff. Remember, these equations, read the headings. Some of these aren't valid for everything. They're only valid for certain things. That's what you need to identify in your either your givens or maybe write keywords or assumptions, okay? Those have got to be important to help you. Is it isobaric? Is it a gas? Is there only boundary work? Then you can kind of jump and say, okay, I know there's a shortcut for that. Okay, let me put this back and let's do a practice problem. Did I make a copy? I must not. That's all right. All right, so let's write this down. I forgot to make a copy. My bad. So write these givens. We'll make a sketch, and I'll talk about what's happening here. So we have a polytropic process. I'm going to write assumptions right here. So polytropic. We're going to find Q. And here is our piston device. Let's assume Q is out. And this expands, so our boundary work is out. So what we have is 4 kilograms of, does it say what gas? No, this says a certain gas. And the process is a polytropic process. It expands out, the piston does. All right. And you have the initial volume, the final volume. There's some change in internal energy between the system. Okay. And we want to find the amount of Q. Okay. So U2 minus U1 is negative, which kind of states that U1 has a, well, higher or lower energy than U2? Higher. Okay. All right. So U1 is higher. And just to give you what that was, so let's get right to the solution. First law. So delta U equals Q in minus Q out plus work in minus work out. And if you want in your assumptions, you could say delta KE equals delta PE, which equals 0. Okay? This whole piston cylinder is not moving in the air or moving around. Just the piston on the right is moving. Okay? But we're not worried too much about that. So here's our first law. Is there any Q in? Oh. Any work in? Oh. And it says, so it says a gas. It doesn't give us anything with pressures. So if it says the gas does that, could assume a perfect gas for another assumption. So if we assume a perfect gas, what can we change delta U to? If we had to. We don't really have to in this case, but we could change it to CV times delta T, right? So just as a side note, delta big U could be mCV delta T. This is mCV T2 minus T1. What did you tell me had the bigger energy, U1 or U2? U1. Which one here? Which is going to have a higher temperature, T2 or T1? T1, because you would end up getting a negative value in here. So I wanted to show you that, oh, okay, we got a higher temperature initially, and it goes to a lower temperature. Okay? All right, but we don't even need to do that. We could just do this. Because we already know what delta U is. Oops, my bad. Equals minus Q out. And we have minus the boundary work. So let's rearrange and solve for Q. Equals, what is it going to equal here? Bring that over. Minus WB minus M delta U. Now, we have a polytropic process, and what is our only work? Boundary. You can go to your cheat sheet and look for the boundary work equation, which should be P2. Is it big volume or little volume here? Big volume. Minus P1 times B1. 1 over 1 minus M. Minus M delta U. What are we missing in this? Do we have P2? No. We can solve for it. Again, we know it's polytropic. We can then say, P2 is P1 times big V1 raised to the N over V2 raised to the N. So, why did I do that? I should, sure. 3 bar times 0.1 raised to the 1.5 over 0.2 raised to the 1.5. You get for pressure 1.06 bar. Multiply that by 10 to the 5th Newton over meter squared. You get 300 kilopascals. And then P1 is, oops. No, that's 3 bar. Sorry, 1 bar was 106. 3 bar converts 300 kilopascals. So again, I could solve for P2, which is right here, because I know it's polytropic. And we know the n is not 0 or 1, it's something else. We can figure, we now have those equations in your cheat sheet you can solve for your new pressure. Now we can plug everything back in. Q equals, I'll have to zoom out just a tad so I know the equation here. Q out is minus P2, 106 kilopascals times 1,000 Pascal and 1 kilopascal times 0.2 meters cubed minus 300 kilopascals times 1,000 pascals over 1 kilopascal times 0.1 meters cubed, 1 over 1 minus 1.5 minus 4 kilograms times a negative, what was it? 4.6 kilojoules per kilogram. And I'll write that down here, times 1,000 joules in 1 kilojoules. Dot, 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 dot. Make sure I got exactly what I had. You get 800 joules. Or it's 0.8 kilojoules. So 800 joules, meaning 800 joules goes out. Okay? So based on this, P1 was 300, right? So if we go up here, that was 300, and we'll do this as kilopascals, and this is meters cubed. This value was 106. This was 0.2, and that was 0.1, right? Just to give you an idea of what happens in a polytropic process as it expands. The volume, oops, that's not right. Why didn't you yell at me? There we go. The pressure from state 1 to 2 goes down. The volume goes up, and the temperature actually will go down based on what we thought was delta U. Okay? That is if this expands and Q was going out. Okay? So, questions on this problem? These are kind of going to be what the next homework's going to deal about. Perfect gas, usually. Or ideal gas equations. All right? So, this is kind of like the vapor dome, but you labeled your pressures, the volumes. Did the sketch, labeled your energies. You wrote your first law, figured out what was going in, what was going out, and then you broke it down into what you could actually then solve for. Okay? So, look at how long now this problem's get. That's why nice and neat, down the page, straight edges are going to help a lot. Okay?
And very small.
No, you can write big. Just go to the next page. I'd rather have you write bigger than tiny where I have to use a magnifying glass. Okay? All right. No questions? All righty.